Okay, thank you very much for the introduction. Hope that you can see me and hear me okay?
Yes.
Okay, that's good. Yeah, thank you for the opportunity to present my work here. It's the title shows my talk basically consists of two parts. First part will be on a continuous vortex wind speed formula. Second part will be how we can apply that to the studies of the internal dynamics, tropical cyclones, via what I call the omega tendency equation. So I work as a weather forecaster in the Weather Prediction Center here in College Park, Maryland. Um, so I've learned a lot of new things by listening to the talks, turbulence, and Dr. Liu's Lutex, and I'm just scratching the surface here. But I haven't really uh, heard a lot about pressure, but pressure is one measure that's pretty important in meteorology. For example, we we the barometer is invented to measure the pressure of the atmosphere. So the most basic forecast is if the pressure is falling, that means a low pressure system is coming and bad weather is coming. So on the screen here, I have three examples of vortices, which are low pressure systems in the atmosphere. First one on the left is what's called the bomb cyclone back in November of last year. This is off the west coast of the United States. Uh, the pressure is very low, down to about 940 millibars here. And the middle is a hurricane. This is Hurricane Melissa back only October, a couple of months ago, made landfall as a Category 5 hurricane over the island of Jamaica. The red dots are lightning locations. Um, on the right side is a water spout. This water spout is about to make landfall on a very highly populated area in Hong Kong. This is back in 2024, September 28th. So, okay, so give you some motivation because I grew up in Hong Kong and hurricanes are one of the big story in Hong Kong in the summer because of the impacts to society and the damage it can cause. So, so I'll give some questions like why should there be an eye in a hurricane, the tropical cyclones? And what are the dynamics associated with the formation or the maintenance of the hurricane eye itself, as you can see here? Um, and another question is, there are other atmospheric vortices around. Do they have the same kind of eye that you can see here? So the part one will be on a continuous wind speed formula, and this will be a classic versus a new formula that I'll show. So the classic model in meteorology is what's called the gradient wind balance, which I'll explain later. And another classic example is what's called the Rankine vortex for specifying the wind speed around a vortex. And then I'll show the derivation of the new continuous formula to specify the wind speed. And then I'll calculate the pressure distribution using the wind speed by integrating the gradient wind equation. And to and the result will tell me whether the central pressure of the vortex would depend on the maximum wind and or the radius of maximum wind. And I'll show some extreme cases of vortices in the atmosphere, how they look in the results. So this is the classic vortex model called gradient wind balance. So this topic is covered in most of the textbooks in meteorology. Uh, this is basically a balance between the centripetal force with the Coriolis force, and this I haven't really heard much mentioned in the conference because I suppose it's a scale. The Coriolis force is related to the spin of the Earth, um, and the right side is the pressure gradient force. So the gradient wind balance is the balance between these three forces. Now, if I think about straight flow, then the R, this term is actually zero because R in this case, a straight flow, the infinity, the radius is infinitely large, that would be straight. So in that case, it would give me a geostrophic winds, meaning the Earth and strophic is the spinning. So it's the spinning of Earth, the wind speed created by the spinning Earth. Um, and in the northern hemisphere, all low pressure systems spin counterclockwise. Now, if I don't consider the V square over R, the the V square over R here, we'll only get the difference between the wind speed and the wind speed of the straight flow. That's what's called the ageostrophic wind speed. And this ageostrophic wind speed is always a negative sign. That means it's going the other way, counterclockwise. And it's always less than the wind speed in the straight flow because it's negative here. Um, So, okay, how should we use a mathematical formula to specify the wind speed around a vortex? So some things to consider here. Well, there should be no wind at the vortex center, and the wind speed should increase outward from the center to reach a maximum some radius away from the center, which we call the radius of maximum wind. And then beyond the radius of maximum wind, the wind speed should trail off to zero and basically to zero out to infinity. So this is the Rankine vortex traditional classical way to represent the wind speed. So basically, it's a combination of a straight line that passes through the origin to 1, 1, and that's where it meets a hyperbola, y equals 1 over x. And this vortex has a vorticity of 2 omega inside the radius of maximum wind. And it's irrotational outside of radius of maximum wind with no vorticity. But one of the disadvantage of this model is right at the peak of the winds, the graph is discontinuous. And if there's one thing I learned from Dr. Liu on Vortex is, well, even though we do not have a vorticity outside of the radius of maximum wind, we know the vortex extends outside of this Rankine vortex, even though it's by design that the Rankine vortex has no vorticity outside the radius of maximum wind. So, okay, here is the continuous wind speed formula I want to introduce is just this simple function x over 1 over x squared. So if I multiply it by 2, it will peak at 1, 1, x equals 1, y equals 1, and then trails off to 0 as you approach infinity, because the x squared would dominate. Um, if I take the absolute value of x, well, now you get a odd function, and you have a peak at both x equals -1 and x equals 1. Now, if I increase the exponent, basically I would make the curve steeper because it's more dominant in the um, denominator. Um, and but the side effect of that is I switch the peak inside less than 1 or greater than -1. So what I can do is to scale the x value and arrive at this formula after I did a lot of math. Um, so I generalize with the Vmax and the radius of maximum wind Rmax. Also, I have this n here, which I call the sharpness factor because that's the exponent of R. So I'm showing n equals 4 on this graph here. And oh, yes, so this graph is showing a spaghetti diagram of different ends. So if I increase n, I get this sharper and sharper curve. But inside the radius of maximum wind, it gets more linear and linear as n increases. Okay, so how can I determine P based on the continuous wind speed formula? So what I can do here is to use the gradient wind equation that has the pressure gradient here. And I combine that with the ideal gas law. And I can integrate with respect to R to get a P. P now is the pressure of the vortex. And P infinity is the background pressure, usually could be 1,000 millibar in meteorology, or the standard atmospheric pressure is about 113 millibars. And if I integrate that R from infinity to 0, I will get the central pressure P at R equals 0. Now, if I integrate the first term using this formula, which is n equals 2, I get this result just -2 times V max squared. So, what does that mean? Well, so it's saying that the central pressure of the vortex using this formula depends only on Vmax, but not Rmax. So it's saying that Rmax doesn't matter. The radius of maximum doesn't matter. It only matter is the Vmax. And that also implies that we do not have a F F is 0, which is the case when F is at the equator, and the F is related to the spinning of the Earth, and at the equator there has not been ever a hurricane ever formed in the equator. So without the Earth, uh, Earth's vorticity, a hurricane cannot form at the equator. Now, so what about the other term? So I if I do the same thing here, integrating, I get a diverging integral, so I cannot get an answer with that integration. So now I increase n to 4 to give me this formula here, you know, fourth power on the denominator. And in this case, I integrate it again, and it gives me a arctangent function using the partial fraction decomposition and gives me an answer. Again, only depends on Vmax. Now, if I integrate the second term here, I, I get an answer, a converging integral here. Instead of diverging, it is a converging integral and gives me a full answer with this formula here to get the pressure at the center of the vortex. So here I plot a graph of that formula. The horizontal lines are actually when n is equals to 2. Um, the slanted lines are the result from n equals 4. You know, that includes the f there. So what you can see is, so given the same Vmax, a vortex with a more gradual wind profile, n equals 2, will have a lower central pressure than the skinny wind profile, like when n equals 4. So this is for a wind max of 40 meters per second. Uh, for n equals 4, you get a higher pressure, central pressure, but n equals 2, you get a lower central pressure when the wind is broader. Now, if I uh, look at for example, if I think of a tornado, the tornado would be a very small scale in the atmosphere, less than 10 kilometers in diameter, even radius. Um, so what is that telling me? 100 meters per second, that's 200, more than 200 miles per hour winds. That's very strong winds. That's telling me that central pressure uh, could be below 800 millibars. That's a very low pressure. Uh, if the wind profile is skinnier and equals 4, that's give me a higher pressure, maybe 870 millibars or so. And incidentally, the strongest hurricane or typhoons ever occurred is about 870 millibar central pressure. That was in Typhoon Tip back in 1979 with a wind speed 85 meters per second. That's when I look back at the graph, this corresponds to n between 2 and 4. So now on to the part 2 of my talk is how you can apply the wind speed formula to the omega tendency equation. So first I'll show the derivation of the omega tendency equation and what does that reveal regarding the internal dynamics of a tropical cyclone and how we can apply the wind speed formula to a hurricane-like vortex and calculate terms in the by calculating the terms in the omega tendency equation, which I call this the control vortex. So I want to clarify between omega and omega tendency. First of all, in meteorology, we use the omega for the dp dt, p is the pressure, and in uh, vertical this is like the vertical motion in the pressure coordinates in meteorology, because when you decompose that, you get a density times gravity times the vertical motion in height coordinates. So this is like the vertical motion, but just a negative sign with respect to pressure, because pressure decreases as you go up. Uh, but I'm talking about omega tendency here is the time derivative of omega, which is like the vertical acceleration in p, and that's the second derivative of p. So they are different, but actually they are related this way. Second derivative of p omega is the omega dt, which is, I call it omega tendency. So, okay, how do I derive the omega tendency equation? I start with the horizontal momentum equation written in meteorology. The simplest way is this way: the Coriolis parameter times the geostrophic wind, which I show in the earlier. And then from that, I derive the divergence equation, and then I combine that with the continuity equation that gives me the omega tendency equation. So I decompose the momentum equation into components, and I differentiate the first equation by x, the second equation by y, and add them together gives me this divergence equation. And from this divergence equation, I combine that with the continuity equation, going through all these steps. And then finally, I get this omega tendency equation. So this is saying that the Lagrangian rate of change of the omega and differentiated with respect to pressure, which is like the height in meteorology, is equal to these three terms, five terms actually. Uh, if I integrate with pressure, assuming it goes to zero when p is zero, I get this uh, definite integral. So, so these we see the same terms in the divergence equation. Um, and what's saying that because of this dp, we integrate that, that's saying that all these terms are integrated vertically through the atmosphere. So anything above you will be communicated downward to where we are all living near the ground. So all of the effects above will be integrated down to where we live. So what are the physical meanings of these terms? Well, I call this first term the vorticity of the geostrophic wind because of the mathematical meanings of vorticity, not the total winds, but the vorticity of the geostrophic wind. Um, the second term, these are equivalent, just in vector notation. I call this solid body rotation because um, its magnitude is more defined inside the radius of maximum wind I'll show. Uh, This term is a divergence square. The square makes it positive always. And, and oddly, there's this 2 factor of 2 here also. And this factor of 2 is also on the next term, which is the vertical wind shear, the change of wind speed with height. And it's the dot product with omega, which is the vertical motion. So it's an interaction between the wind shear and the vertical motion. And the last term is kind of a standalone term related to the Coriolis force. So this is the control vortex that I'm talking about using the wind speed formula with n equals 2. I put this formula into a 100 by 100 kilometer grid. So it gives me this vortex here, which is counterclockwise in the northern hemisphere we're living in. And I specify a maximum winds of 50 meters per second on a radius of 20 kilometers from the center of the vortex. So, um, so this is showing the same plot I have, but with the uh, plot of the wind speed and saying this is a low pressure system. And yeah, one thing that we haven't mentioned in this talk is about the pressure. So now I integrate the pressure from kind of zero out to infinity or the other way around, like still get the same answer. If I try to just use one for the density to interpolate the pressure, get this profile, that gives me a central pressure of 949 millibars. Now, if I use the exact formula that I've shown to Vmax squared divided by R and temperature, you get a lower pressure, central pressure 944 millibars. So now um, I want to compute the first two terms in the omega tendency equations using the wind speed formula in the grid that I've shown. So what I got is this: the vorticity of the age-Stover winds. I get this circular plot, but inside the radius of maximum winds, they're all negative values. Now, when I plot the other term, I get almost exactly the same figure, except that everything inside is positive. So, okay, same circular shape, but opposite sign. So what if I plot the graph together? Well, I get the red curve almost exactly the same as the blue curve here, which would represent the second term. So, okay, so do they actually overlap? So I subtract or add the two together. I get this almost zero line. There's a little bit of waviness here. It turns out it's because I use a numerical approximation. Um, that gives me a little bit of numerical errors with the uh, you know large change in wind speed, radius maximum wind. And then the question I have for you all is, so if the winds are not in, so what if the winds are not in gradient wind balance? Do do I get a zero curve? Do they cancel each other, these terms? So to answer that question, I introduced this formula. Basically, I multiply this number, a number I call super gradient factor. Just multiply this number to the winds, and it gives me a modified version of the geostrophic wind. Um, so if the number is greater than one, that would give me a wind speed, bigger than the normal wind speed. So that would be a super gradient winds because I use the gradient wind formula here. So if it is more than gradient, it's the super gradient. The opposite is true. If it is less than one, that would be a subgradient. Now, if I use a 1.25 factor, supergradient factor here, what do I get here? I get the first term, yeah, bigger than the second term because I use the bigger wind here. And when I subtract these two terms, what do I get? Well, I do get a negative number inside the radius of maximum wind, but a positive number outside of the maximum radius of maximum wind. So it depends on where you are with respect to the radius of maximum wind. It is negative inside, but positive outside. I put a negative sign to uh, give it a convention like you normally would for a height coordinates. So what that means is there's a strong tendency for air to sink, to move downward um, inside the radius of maximum wind and is maximum near the center of the vortex. But there's some tendency for air to rise outside of the radius of maximum wind. So keep in mind, we are talking about the winds beyond super gradient for the entire vortex. Now another try is what if I increase the n to a lot bigger number? So that would give me a more pronounced rise and fall of the wind speed. And lo and behold, I get a more pronounced rise and fall of the uh, d omega dt minus d omega dt, and that would give me a strong sinking tendency inside the radius of maximum wind. But it moves closer to the radius of maximum winds, and it doesn't change all that much near the center. But outside of the radius of maximum wind, there's a big jump in the positive number here, which means a lot of rising motion. So what this is telling me that this looks like what's happening in a hurricane, a strong tendency for air to rise near the eye wall, but no clouds inside the eye. And another uh, possible effect is the strongest tendency is just outside of the radius of maximum wind. So does that mean that the hurricane is slope outwards as you go further up, which observation suggests it is? Now, if I do the opposite, I specify a number less than one subgradient wind, I get the opposite. I get a lot of rising motion tendency inside the radius of maximum wind and some sinking tendency outside. And again, if I specify a larger n here, I get a more pronounced ups and down around the radius of maximum wind. And is that showing what a thunderstorm uh, would be like with a sinking motion outside of thunderstorm, a lot of rising motion inside of thunderstorm? That's a question to be answered. So I'll summarize the main findings here. So the omega tendency reveals a dynamical link between the A gradient winds with the vertical motion tendency in a curved flow, such as a vortex. So a vortex with a super gradient winds has a strong tendency for subsidence to develop inside the radius of maximum wind, like an eye in a hurricane. And it has a tendency for ascent to develop just outside of the radius of maximum wind, like in the eye wall. And the opposite is true of subgradient winds. You have a strong tendency for ascent inside the radius of maximum wind, but subsidence outside of the radius of maximum wind. And if we do not have any uh, differences or the winds are in exact gradient wind balance, then there's no tendency for vertical motion to develop at all. So the omega tendency equation, I've only time to explain the first two terms. Um, the other two terms about the divergence and especially the wind shear, they have been studied in severe thunderstorms. And in hurricanes, the wind shears are basically considered bad, it causes weakening. But it is opposite for tornadoes. They like wind shear. So I do not have time to go into the details for the last three terms in this talk. And for future work, um, I'd like to include the thermodynamic equations, see how that can have insights into the omega tendency equation using the height coordinates. And I'd like to derive the omega tendency equation in cylindrical polar coordinates for an axisymmetric vortex, such as, a lot of vortices in the nature is axisymmetric. And what are processes responsible for producing supergradient winds that would give us, that kind of ups and downs in the vortex? And are there potential application to other, atmospheric phenomena such as water spouts, tornadoes, and jet streams? And the final slide, I would like to show you a video of the water spout that occurred in Hong Kong just last year, just for you to marvel at this. It's very close to a high-rise building. This was taken by some family in a high-rise building, which is very good vantage point. And at the same time, I can answer any questions